In this video, we're going to talk about the characterization of planar graphs. Now, as many of you know, this is known as Kuratowski's theorem. Kuratowski's theorem will take many videos to prove, so it's not really the scope of what I'm trying to do here. But in this video, I'd like to talk about what Kuratowski's theorem says and build up to it so that we see why it makes sense. First, remember from the previous video that K33 is non-planar and K5 is non-planar. Also, it's pretty clear that if a graph contains a non-planar subgraph, then it's also non-planar. Let's take a look at a specific example of this. So here I'll draw a graph G, which looks remarkably like K5, but it has some extra stuff going on. So there's an extra vertex and a couple of extra edges. But notice that because it has K5 as a subgraph, this graph G is also non-planar. Because if you could draw the graph G in a planar way and then just remove those extra edges and that extra vertex, then you would have a plane drawing of K5. But we know that that's not possible. So that's why we know that this statement holds in general, that if you have a non-planar graph as your subgraph, then you cannot be planar. But more is true than this. Let's take a look at a different example. So here I'm going to draw what again looks like K5, but now I'm adding a new vertex, not in the same way that I did before. The new vertex interrupts an edge that used to be in K5. So in this purple graph, K5 is not a subgraph, but it's still true that this graph is non-planar. And the reasoning is similar. If you could draw this graph in a plane drawing, then all you would have to do is remove that one vertex that lies on the line and replace it with just an edge. And then you would have a plane drawing of K5. So this graph G in purple is also non-planar, but it's not because K5 is a subgraph. It turns out that this graph G is what's called a subdivision of K5. So it's important to study subdivisions because we can obviously see in this example that a subdivision of K5 is not planar. So those are going to be important to understand. First, we define an elementary subdivision of a non-empty graph G to be a graph obtained by taking an edge in the original graph G, call it E equals UV, removing that edge and adding a new vertex W and two new edges, UW and VW. If we look at the example graph in purple, we can think of this as having started off as K5, and then we have the edge UV as marked in red, and we've removed that edge, instead put in a vertex W and replaced it with edges going from U to W and also from V to W. So in particular, this graph G is an elementary subdivision of K5. To make sure that we're comfortable with the definition of an elementary subdivision, let's look at another example. Here I'll draw a graph G, which has only 4 vertices, and I'm going to choose a particular edge that I like. So I'm going to label its ends as U and V. Now, an elementary subdivision using that edge is going to say remove that edge and then put in a new vertex. So let's start. We'll redraw the graph, but now we have that edge removed. Now we put in a new vertex W and two new edges that go from U to W and also from V to W. So essentially it looks like we've just added in a new vertex onto an edge, and that's basically the intuition behind it. But we have to describe it in terms of removing an edge and adding in two new edges with the new vertex. Next, we define a subdivision of a graph G to be a graph obtained from G by a sequence of 0 or more elementary subdivisions. So let's try another example. I'll draw a graph G in blue here, and notice that G is obtained from itself by 0 elementary subdivisions. So in particular, a graph G is a subdivision of itself. Next, we may want to take a look at doing an elementary subdivision. Suppose we do an elementary subdivision on the top edge, and we get a new graph. Let's call the new graph G1. So it happened after one elementary subdivision. And the new vertex and the new edges I have represented in purple. But now this is just a graph, and we could perform another elementary subdivision on any one of the edges we like. So again, I'll just pick an edge and I'll do another elementary subdivision. to get the graph G2, and notice that G2 is an elementary subdivision of G1. G2 is not an elementary subdivision of the original graph G, but it was obtained from two elementary subdivisions, so we call it a subdivision of G. We can also keep taking elementary subdivisions of any edge we like, so I'll do one more to represent G3 as yet another elementary subdivision that we've obtained, in this case from G2, and now all of G, G1, G2, and G3 are known as subdivisions of the original graph G. And we could have done this in many ways. This is just a particular example. Observe that any subdivision H of an original graph G is planar if and only if the original graph G was planar. This makes perfect sense because subdividing an edge does not change the planarity of the graph. In particular, we know for a fact that K5 and K3 are not planar. So then we know that if a graph is a subdivision of either one of those graphs, it is definitely non-planar. So now imagine that you take K5, for example, and you build up a subdivision of K5. Clearly, that graph, being a subdivision of K5, is non-planar. But moreover, any graph which contains that subdivision of K5 also cannot be planar. So it's not just subdivisions, you can't even have a subdivision as a subgraph. Then you would ruin planarity. To say this more precisely, as a fact, if a graph G contains as a subgraph a subdivision of K5 or K3, then the graph G is non-planar. So far, I think everything we've talked about has been pretty intuitive, and this fact should make perfect sense. But the surprising thing is that yes, these graphs, which have subgraphs that have a subdivision of K5 or K3, those are non-planar, but they are the only ones that are non-planar. And that amazing fact is what's known as Kuratowski's theorem. Kuratowski's theorem tells us that a graph G is planar if and only if it contains no subgraph which is a subdivision of either K5 or K3. Remember, the obvious or clear part of the theorem is the part that says if you have a graph which has a subgraph that is a subdivision of either K5 or K3, then clearly that graph is non-planar. The really fascinating part is that as long as that doesn't happen in your graph, then your graph is planar. Now to prove that, it would take many videos, so it's beyond the scope of this video. So hopefully now you have a good understanding of what a subdivision is and what Kuratowski's theorem means. Check out these related videos and I'll see you next time.